Today we're going to talk about binomial tables, and we're going to show how to do a lot of work very quickly when we have events that have more than one outcome. So start today looking at the tables. Okay, the assumption here, we have a x is a binomial random variable with 4 trials and a probability of 0.3 of success, and we want to calculate the probability that x is equal to 2. Okay, this is how we do it. We have a set of tables, and these are located on Canvas. You should be able to find them. And the tables have the binomial values for different values of n. I think we have n that goes from 2 all the way up to 20, and different values of p. We have them going from 0.05, 0.1, 0.2, all the way up to 0.95. Here, okay, we have our p-value of 0.3, so we're going to look over here. Okay, we have our n value of 4, and so we look in the ends here at the 4s. Okay, and then we have, among the 4s, we pick out the particular one, little x equal to 2, and so we follow that over, and this allows us to look up the value 0.265, and this is exactly the same value we would have gotten if we had put in all these numbers into the formula and cranked it all out. Okay, but as you see, it's just a table lookup. All you have to do is look up the table, and that's a lot easier, a lot less computational, provided you actually sit down and learn how to use the table. So let's start off here with an example. We have 5% of the gravel in a 50-pound sack has been replaced with diamonds. Yet, so this is a realistic example. What is the probability that in a sample of 15 pieces of gravel that it will contain between 1 and 4 pieces inclusive? That inclusive means you include the 1 and the 4. So let's see how this plays out. Okay, well, again, from reading the problem, x is a binomial random variable, sample size of 15, and a probability of 0.05 for success. We're looking for the probabilities that between 1 and 4 inclusive, so this includes 1 and 4, and so we'll do x equals 1, x equals 2, x equals 3, x equals 4. We could just, okay, plop these numbers into the formula like I have here and do the calculation. Okay, we could just do that. I mean, the formula's here, all we would have to do is run it. But why not instead go to the table? We have the value with n equals 15, and we're running it between 1 and 4. So 15, probability of success 0.5, between 1 and 4, and so we run out these particular numbers and we do the sum, and that works out to 0.537. Okay, about almost 54%. Okay, example 2. A disease known as I-got-a-potty-itis is rampaging through the town of Heartland, Kansas. At a particular cocktail party, 10% of the people present are contagious, but not yet symptomatic. A local politician shakes hands with 9 people, reasoning that only 1 in 10 people has the disease, so he should be safe. what is the probability he has shaken hands with at least one infected person? Well, okay, so it's a binomial random variable with 9 trials, right? Shaking hands with 9 people. Each one of them has a 10% chance of having the disease, okay? And so what is the chance that he has shaken hands with at least one? Okay, well, the probability that X is greater than or equal to 1. Now, 1, 2, and 3, and 4, and 5, and 6, and 7, and 8, and 9. And you do the table lookups for all those probabilities. And so, okay, this would have been 9 fairly nasty calculations if you had done it by hand. Now, the upside of this is after a certain point, it gets to where it rounds off to 0. Okay, so the arithmetic gets a little bit easier. So we get 0.612 probability. But this is method 1. This is actually a special case which, if you're a little clever, you can make it much, much easier. Okay, what we notice here, right, is that we've included every value but 1. If we take all of the probabilities together, you know, everything possible, that adds up to 1. So the only event we're excluding is the probability that X is equal to 0. We do the table lookup for X equals 0. We do 1 minus that, and we get 0.613. Now, there is a difference in the last decimal place, but that's due to round off error, and it's, you know, it's only 1 in 1,000, not a big deal.